started recording your class. So, in case of then organic chemistry, we know that the ortho, meta, para substitutions are there with respect to any other substituents, and that is the geometrical isomers. Then conformational isomers are also there, which is known as the chair and board conformation. Optically active compound like the D form and L form, we have just now discussed regarding these things. Now, in case of the inorganic complexes, coordination complexes, basically there are so many types of different isomerisms we can find out. So, what does the isomers mean? Isomers means, okay, isos means the same kind, okay, and then the meros means the parts. That means the same number of same kind of atoms are present. So, definitely the molecular formula of the two compounds means the isomers will be the same, but it will be different somehow, in its either in its positions or some other chemical properties possibly, okay, or the physical properties as well. We are just going to observe those kind of deviations of the properties. So, ionization isomerism. Then the first one, in case of the coordination complexes, we are just going to have different isomerism. So, this is known as the ionization isomerism. So, the name itself will tell you that the ionization isomerism will occur. That means after ionization, it is going to form, different sorts of counter cation and anion. So, let's give some example, then only it will be understandable to you. So, cobalt, Br, then NH3 whole 5. We know how to write down the coordination complexes that we have already discussed. That first you have to put the metal, and then the anionic donor ligand, and then the neutral ligand you have to put. And first the cationic part, and then the anionic part, obviously. So, this one. And then the other one compound like the SO4, NH3 whole 5, and then the Br. So, you see the same number of same kind of atoms are there in these two complexes, but whenever they are just going to dissociate, it is just going to form this one, that cobalt, then Br, NH3. So, this will be positively charged, and SO4 minus will be the negatively charged, okay, SO4 2 minus. In this case, it will be Br minus and this complex entity, okay. So, cobalt is in the plus 3 oxidation state. So, this will be in the positive oxidation state. So, you see here now, due to the ionization, you can just find out the sulfate anion as well as the bromide ion in the other cases. And you can, if you just add the AgNO3 solution, how do you know this one? If you add AgNO3, then it is just going to give you the precipitations of AgBr. In this case, if you add the barium chloride solution, then it is going to give you the barium sulfate precipitation. So, from here you know that due to the ionization, it has formed different sorts of ions. So, that means inside the coordination zone or the first sphere of coordination zone has a different ligand which is ligated to the metal center. In this case, bromide was ligated to the metal center, but sulfate was outside the coordination zone, and it will just act like an anion. But in case of this compound, you see bromide is outside the coordination zone, whereas the sulfate is ligated to the cobalt center. So, you cannot get the test for the sulfate ion in case of this compound, and the similar will be true. You cannot get the test for the AgNO3 solutions if you just put. So, it is not going to give you the precipitations of the AgBr. So, that will say that Br is inside the coordination zone, not outside. Now, there is another, physical properties differences we are just going to get. If you just measure the conductivity measurement, okay. So, conductivity measurement if you just perform, then we are just going to see this will act like a bivalent electrolyte. But in this case, we are just going to get this one as the univalent electrolyte. So, these two things will tell you that due to the ionizations it forms a different sorts of complexes. So this is
Sir, why it is univalent electrolyte means how is it differentiated?
how is it? Univalent electrolyte means conductivity measurement. Okay, it depends on in which solvent you are measuring the conductivity, and then there is a range of the conductivity. For the univalent electrolyte, the conductivity will be less than the bivalent electrolyte. So bivalent electrolyte conductivity will much more than the univalent, and there is a range. In research papers, you are just going to find out in different solvents. People have taken different sorts of electrolyte like the univalent, biunivalent, triunivalent electrolytes, and then they have measured in a particular solvent at a particular temperature, means like let us say the room temperature, and then there is a table. So from that table, if you just take one unknown compound and then measure the conductivity similar way, taking any other solvent, means like the acetonitrile solvent or in water in this case maybe, okay, and you are just going to find out in which range it is just going to fall, whether it will be univalent, biunivalent, or bivalent, or triunivalent. Okay, so that is the case. So in this way, you can just find out the conductivity by measuring the conductivity. You can find out that which source of counter cation and anion it has been dissociated in solution. So that is known as the ionization isomerism, and there are several other examples are also there, like. Okay, just 1 minute. I have the page here possibly. Just okay. So here another example. So this is the cobalt Cl2 and then NH3. Obviously it will be whole 4, and then NO2 was there outside. And here cobalt Cl, then NH3 whole 4. I think in before this one I have to put the NO2. Okay. And then Cl. So here AgCl precipitations will occur, but in this case AgCl precipitations will not occur. So in this way you can just figure it out that whether it is correlated to the metal center or not. So that is ionization isomerism. Now hydrate isomerism. So different sorts of isomerism, we can just ask you, give some examples of what does this hydrate isomerism, ionization isomerism, or some other kind of isomerism, whatever I am just going to discuss today. So those type of isomerism occurs, and give some examples, and then there are differences in properties, either chemical or the physical properties. Okay. So hydrate isomerism is another type of isomerism that may occur. So this is the second type isomerism. So this ionization, okay, this isomerism arises out of different dispositions of the water molecule within the first pair of attractions or outside the coordination zone. So there will be some sorts of variations of aqua ligation either towards metal or it is outside the coordination zone. Like I am just giving you the example, CrH2O whole 6, okay, all 6 water molecules are ligated to the metal center and chloride is outside. How can you figure it out? And this is violet in color. So it will give you the AgCl precipitation. If you just keep this compound in presence of concentrated H2SO4, not lose its weight. Okay, simply if you have a compound like I have given you copper sulfate pentahydrate, if these water molecules are not ligated to the metal center, simply present as solvent of crystallization. So let us say, so this is known as the solvent of crystallization. Sometimes you will see, different amount of solvent molecules are in between the, the crystal structures are there, and those are loosely bound, not directly bonded to the metal center. In those cases, if you just have a vacuum desiccator, let us say this is the vacuum desiccator, okay, and you have a lid over here, and you can put the vacuum like this way. There is a knob, okay, so this will be the vacuum. Okay, you can put vacuum through this one, and then if you just keep like here in a beaker, so this will be the concentrated H2SO4, let us say. So this is the concentrated H2SO4, which is highly hygroscopic in nature. It can just take water molecules from some other compounds if it is not directly bonded to the metal center. And here is your compound, okay? Compound dot, let us say H2O molecules are there. So your H2O will just move, towards this one H2SO4, and it will just quickly absorb. So you are just going to get your compound a very dry compound. Okay, if it just absorbs moisture from the atmosphere, then in order to dry it, you have to put some of that solid in presence of the concentrated H2SO4, and then you can put vacuum. Okay, little bit vacuum will be fine for this one. So it is then going to lose, its weight. Whatever compound you have taken here, and then if you weigh that compound, how much amount is left after drying this one, from there you can just say whether these water molecules are just like the solvent of crystallizations or are coordinated to the metal center. If these are coordinated to the metal center, these are not going to lose. Okay, so the weight loss will not take place in that case. But in other case, if the water molecules are present outside, then some sorts of the weight loss will take place. And here I am just going to show you the other examples. So other examples means like this is blue green in color. So this one is Cr, Cl, and then you have H2O molecules 5 number inside the coordination zone. Outside the coordination zone, you have the 2Cl2. There was a mistake, okay, so this was Cl3. So 2Cl2, and then one water molecule is outside the coordination zone. So this is going to loses one H2O molecule in presence of concentrated H2SO4, and also if you just react with AgNO3 solution, in this case 3 equivalent of AgCl precipitations occurs, and in this case you are going to observe instead of 3, it will give you the 2 equivalent of silver halide precipitation. You can weigh these precipitates, whatever AgCl precipitates you got, you can just filter it through a G4 frit, and then that frit will obviously be weighted before and after filtrations. After properly drying, you can just weigh that one, and how much amount of silver halide precipitations occurs, you can get some idea out of that one, that whether 2 equivalent of silver halide or 3 equivalent of silver halide precipitated out. So these are the differences, and you can see this is blue green in color. So this one is blue green in color. So one thing you just observe here, if there is any change in the coordination zone, then there will be, or if it is expected that there should be some sorts of color differences, and it depends that how much. Later on I will just discuss that crystal field stabilization energy. I have not reached it yet at that part. Okay, during the crystal field stabilization energy, we are just going to see the 5 degenerate orbitals are going to split in 2 sets of orbital. One is known as the T2G, another is the EG, and the energy difference between this T2G and EG set of orbitals is known as the crystal field splitting parameter. So it depends on this crystal field splitting parameter where from the color is originating. If it is DD transition from T2G, electron is transformed or excited to the EG set of orbital. And then if your gap of the T2G and EG set, that is known as the crystal field splitting parameter delta, if it increases or decreases, depending on that, you require different means energies light in order to get it absorbed. So obviously your color will be different in those cases. But if you see, if your H2O is there, and now suppose there is some other molecule like the methanol molecule, let us consider. Okay, so methanol molecule O is coordinated to that one. We are not going to observe that crystal field splitting parameter any appreciable variation, so you cannot expect the color change as well. So it depends that which kind of ligands are getting substituted within the coordination zone and outside the coordination zone. Okay, which molecules are there. Similarly, in case of this compound, we are just going to find out another one. So this is the H2O whole 4, and then you have the Cl 1 Cl and 2 water molecule. So if you take this compound in presence of concentrated H2SO4, we are just going to see that here, 2 molecule of water loss takes place. In this case, here 1 molecule of water loss takes place, because you can just calculate the molecular weight and how much you are going to expect. Molecular weight calculations, you have some idea how can you calculate the molecular weight. And then if you see 1 water molecule loss takes place, then how much will be left in this part. Okay, so and you are just going to get that part, okay, after means getting your water molecule out from that compound. In this case, 2 water molecule and 1 silver halide precipitation will occur. So in this case, only 1 AgCl precipitation, here 2 AgCl, and that 3 equivalent of AgCl precipitations will occur. And as well as we are just going to get some weight loss. In this case, no weight loss will occur because all the H2O molecules are coordinated to the cobalt chromium center. So those are not easy, or those are very difficult to snatch it out from the metal coordination, metal coordinated zone. Okay, so that's the case. So there is another complex. So this is known as the quinaldinic acid. So this is quinaldinic acid. So 2 fused rings are there. One is the pyridine nitrogen, and then you have the C double bond O, OH. So if it's get deprotonated, then it is just going to give you N and O minus donors. Because if it is correlated to the metal center, how many member of ring it has been formed? You can see here from starting from metal, 1, 2, 3, 4, 5. So this is 5-member ring it is going to form. So it will be highly stable, but it is not going to coordinate through this oxygen atom, because this oxygen atom, if you just make then 1, 2, 3, 4, 5, that is also 5, but it depends on which is negatively charged. Always metal, if it is present in the higher oxidation state, it will prefer to deprotonate this acid. Okay, because you can just think of metal is in the positive oxidation state and proton are also in the positive oxidation state. So instead of proton, so proton and metal, and those two are competitors of each other. Sometimes you do not have to add some little bit amount of base. In this case, you can add like NIT3, so that can act as a base, and it is just going to form the metal compound, and NIT3H plus. Okay, NIT3H plus, it is just going to form if you have the proton. So proton, if you add, then definitely that has some negative charge. Like let us say HCl, if you add, then it will be NIT3HCl, because H plus Cl minus if you add. Okay, so H plus and Mn plus, those are competitor to each other. Even if you do not add any base, it is going to deprotonated by the presence of the Mn plus, because M metal is in the higher oxidation state, and automatically it will get deprotonated. So this is the compound. This is known as the HQ. We can just like, so this is the quinaldinic acid. And if it gets deprotonated, it is just going to form Q minus ligand. So otherwise it will be said HQ. H means the dissociable proton. So you can just make the two complexes, VO, then Q2 dot H2O. This is olive green in color. So this is olive green in color, and the other one is VOQ dot H2O will be outside. Okay, so dot H2O will be outside. This is cream color. So vanadium will prefer, it will be pentachlorinated. Oxovanadium, this is known as the oxovanadium. So this one ligand and another ligand, square pyramidal coordination geometry, and one will be N, another will be O. So this one and NO. Okay, I am just writing in this way. This is in cis positions, but this may be coordinated via the trans behavior as well. Okay, you can think of like this one. Those things will also come later. Okay, so if you just consider this one N, this is N, this is O, this is O. Now the ligands might be like this way. So this is in cis conformation, but this is in the trans conformation, the O donor centers you can just think of. So thermal decomposition curves, if you just do the PGA DTA means experiment, okay. Thermogravimetric analysis means you are just heating your sample and then you are just going to observe the weight loss. So suppose you are heating, so the temperature we are just going to increases, and here is the weight of that compound. So like let us start, here is the molecular weight, suppose 300, okay. So 300 it will go. So this is 100 degrees Celsius temperature. Till 100 degrees centigrade temperature, no weight loss takes place, and suddenly you are going to watch the curve will go down, and then again it will be like this way. So that means here at this temperature, okay, it is just going to lose one water molecule, and then whatever weight loss will take place, you can measure that weight loss by doing that experiment, and that will be equivalent to one water molecule loss from the compound, okay. So in this way, then we can just see that as in both these cases, one water molecule is here. So whenever one water molecule is there, at that time its structures will be like hexacoordinated, but in the other one it is the pentacoordinated. So pentacoordinated or hexacoordinated. So the coordination zone change takes place, and we know later on we will see that depending on the coordination geometry adapted by a metal ion, the d orbital splitting, 5 degenerate d orbitals splitting will be different for different coordination geometry. So if the splitting is different, then the T2G set, EG set, or the electronic transitions of whatever takes place depending on the metal ion, how many number of means electrons are there in the d orbital, depending on that your color will be different. And we are just going to observe here, one is olive green in color, but the other one is cream in color. So these two are then the ionization isomerism, hydrate isomerism we have already covered. Now I am just coming to the coordinate isomerism or coordination isomerism. Coordination isomerism, you can see from the name that definitely the coordination zone ligand exchange will take place, and both the cationic part as well as the anionic part is coordination complexes or are coordination complexes, okay. And they are only the redistributions of the ligands will occur. So if I just give you one example, so this is third type. So cobalt NH3 6. So let us say cobalt is in the +3 oxidation state. So this will be as a whole 3 plus, you require 3 minus, which is oxalate whole 3. And here again it is chromium 3 plus. Oxalate means oxalic acid. So C double bond O, O minus. Here is the double bond O, and that is another O minus double bond O. So this is the oxalic acid. So if chromium is there and +3 oxidation state, and if you have 3 number, means like this one and this one, so here is 2 minus and 2 minus 6 minus charge. So ultimately it will be 3 minus charge, and these are going to be electrically neutral. So this one compound you can make, and another compound, let us say just after redistributing the ligand, whatever we will get, those two are going to give you the isomers. So that will be then the chromium NH3 6, because cationic part you have to write down first, and then it will be cobalt, and then oxalate whole 3. So this is now 3 minus, and this is that. So what happens? The redistributions of the ligand occurs in the solution phase, or in these two complexes. And whenever you will just going to dissolve this one, if it is labile, that means the binding of the ligand with the metal center are not so strong, then it can exchange the ligands in solution phase. But you have isolated these two complexes in solid state. That means your cationic part and the anionic parts, you can easily see from the X-ray structure determination that oxalate anions are coordinated to the chromium center in this compound, but in the other compound, oxalate anions are coordinated to the cobalt center. So this is one example, and several other examples are also there. Just I am writing. this one, and then you have the chromium Cn whole 6. So the other one will be definitely then that will be the chromium NH3 whole 6, and then the cobalt Cn6. So this is another example. Copper also examples are there, and there might be several other examples you can find out, but we require only one or two examples you have to give, and then what does that mean you have to discuss in your exam paper if the questions comes. So NH3 whole 4, and then copper Cl4. Okay, so platinum is in the +2 oxidation state, copper is also in the +2 oxidation state. Now you can think of what happens. So the cation and anion, okay, will be different in these two complexes then. But suppose if you can make a compound where both the metal centers are same, then it will be very difficult whether you are going to get some other isomers or not, because even if the ligand exchange takes place, as the cation as well as the anion of that compound contains the same metal ions, you will not have any idea whether any ligand exchange takes place in the solution phase. But if you just make a solution of this type of complex, then if you want to watch whether ligand exchange occur or not, then you can just easily find out that ligand exchange occurs or not. Okay, whether the oxalate anion leave the chromium 3 center and prefer to bind to the cobalt 3 center, okay, and give you some, a different, complex or its isomers like this way. So that is one. Then the fourth number is the ligand isomerism. So there are different sorts of isomerism. It's not like the organic compound. In case of organic compound, we are just going to find out ortho, meta, para. Okay, so the geometrical position and conformational, chair conformation, boat conformation, and if the optical active compound, then D form and L form. Here we have plenty of different sorts of isomerism that may occur, and here are the examples. So ligand isomerism is telling us that if your ligand itself is, behaves like a isomer. Like I am just going to give you two different examples of the ligands which has the similar composition, means like the molecular formula CH3 whole 3 and then NH2. So this is known as trimethylene diamine. So this is trimethylene ethylene diamine. Trimethylene diamine. And another one we can think of that if it is like, if we just draw in this way, CH2 and then CH, NH2 and then CH3. Okay, so you have 3 number of carbon atoms. So CH2, CH, CH3, and here CH2, 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 and 2 ammonia, amine groups are there. So this can be abbreviated like tin, PN, and here propylene diamine. So this is the propylene or we can just abbreviate it like the PN. Now, if you can make the two complexes like cobalt Cl2 PN whole 2 and then one chloride will be outside, and in the other compound, these are the isomers, cobalt Cl2, instead of PN it will be TN whole 2 and Cl. So that means there is no change due to the ionizations will occur. Here AgCl precipitations will take place, AgCl precipitations will take place in both cases. Okay, in both cases you can see that the coordination will occur, either via the PN, that is a different ligand than the PN. Okay, so PN and TN, so only the difference is present within the ligand periphery or the ligand structure. In this case, it will be said propylene diamine, and the other case it will be said the trimethylene diamine TN or PN. So these two are isomers which isomerism occurs due to the differentiations of the ligand structure. Similarly, the picolinic acid and nicotinic acid. Picolinic acid means this is pyridine. So pyridine, if you have the alpha carboxylic acid group, so this is known as picolinic acid. This is the common name. And another is if you have the carboxylic acid group in beta carbon atom, C double bond O, O, H. Okay. After deprotonation, it is just going to give you O minus. Here also the same thing. And whether it is going to coordinate with the same metal center or not, you can just think of like this way. Okay. So 1, 2, 3, 4, 5, 6. So this is 6-member ring. But in this case, if it is coordinated to the metal center, then it will give you the 5-member ring. Both 5 and 6-member rings are stable. So this is the picolinic acid, and this is known as the nicotinic acid. And we can just have the complexes like Ag, picolinic acid will be abbreviated like PIC, so PIC2, and Ag, NIC2. So that means both of these complexes have same number of atoms are there in these two complexes, and that's why these are isomers. However, we have a change on the ligand structure. Here there is no change in the functional group, and as well as the pyridine moiety, both are there, but the geometrical positions of the carboxylic acid groups are different. In this case it is ortho, but in this case it is in the meta position. But if it is in the para position, then you are not going to form any metal complex, considering one ligand where the pyridine nitrogen and the carboxylate one of the oxygen atom will be attached to that one, because that is going to give you 7-member ring. It will better to prefer like acting as a bridging ligand. So this N will coordinate to the one metal center, and the carboxylate O minus is going to refer to the other metal center if it present in the para position. So this is picolinic acid where it is alpha carbon atom substitution, and this is the meta one, that is the beta carbon. If substituted by a carboxylic acid group, then it will just generate the nicotinic acid, and these two acids is going to form the same complex with the means the complex with the silver plus ion. Okay. So then ligand isomerism, I hope that it is easily understandable. Then the linkage isomerism, so that is the 5 number. There are different sorts of linkage. So whenever you are just considering one source of isomerism, then you have to think of that in all other parts it should not fall into the other one too. Okay. Linkage isomerism means only there will be a difference in the linkage, but you have the same number of same kind of atoms, and it is telling us that you have to have an ambidentate ligand. Ambidentate ligand means one ligand which has more than one type of donor atoms, and it may coordinate either one of these two donor atoms to the metal center. Then it is just going to give you the linkage isomerism. Suppose we know that NO2 minus, so that can coordinate either via the N or via the O minus. So either one of it is if it's used, like suppose I am just giving you example like the cobalt and then NO2, I am just writing down underneath this one through which it is coordinated. In this compound, it is coordinated via the N atom, and then you have the NH3 whole 5 and Cl2. NO2 is 1 minus charge and Cl2, so cobalt will be in the +3 oxidation state here. Okay, and this is yellow brown in color. And another compound you might have like cobalt, then ONO. Okay, it is coordinated via its oxygen donor atom, and then the other remains the same, exactly same. So there will be no differentiation due to the ionization. Okay, ionizations will produce 2 equivalent of chloride in both cases. Only the difference is here the nitro and 5 ammonia molecules are present, so both are there, but only the changes occur within the ligand systems. Okay, within the ligand system means via which atom it is coordinated to the metal center. In one case it is nitrogen donor, and in other case the nitrite will means give you the oxygen or act like an oxygen donor ligand. So these are the two cases, and this one is red in color. So there is some color differences, and it is obvious that you can expect color difference because here the coordination zone, the donor atom has been changed. In this case 5 and 1, so 6 nitrogen donors were there, but in this case 5 nitrogen donor and 1 oxygen donor is there. So the crystal field splitting parameter will be different, T2G2 EG gap will be different, and you can expect different colors. Okay, so that is one of the reason giving you the color of the coordination complexes. That is the DD transition. Others are the charge transfer transitions. That color part we will just discuss later on. So here one example I am just going to give you. That example, like if you have the K2 palladium SCN whole 4 S, it is coordinated via S atom. Then if you have the bipyridine, and if you just do the reaction at minus 78 degrees centigrade, so minus 78 degrees centigrade means dry ice and acetone. If you make a slurry, that is going to give you minus 78 degrees centigrade, and we are just going to observe a complex compound will be formed where it is just going to coordinated via the thiocyanate, but the two thiocyanate anions will be replaced by a bipyridyl ligand. Bipyridyl will act as a chelating ligand. So monodentate ligand you can easily replace by other ligand which is polydentate if it forms 5 or 6 member ring with its donor atoms to the same metal ion. Then that is known as the chelate effect, and due to the chelate effect, the stability of that compound will be more than if it is coordinated to the only monodentate ligand. So here two of the thiocyanate anions will get exchanged by the bipyridyl ligand, which is a bidentate one, and this is orange yellow in color. And here the thiocyanate anions are coordinated via the sulfur atoms. Now if you just heat this one 150 degrees Celsius temperature, you are just going to get a different compound where the ligand, donor atoms going to change in this complex. Okay, and this is light yellow in color. Okay, and you can make this compound by one shot, not going through the orange yellow isomers. If you just consider K2 and then palladium SCN whole 4, here S coordinated, then bipyridyl, and if you just have the reaction at room temperature. So if you do the reaction at room temperature, you are going to be ended up with a compound where thiocyanates are coordinated via its nitrogen donor atom. But in the other case, if you just do the same reaction at low temperature, we are just going to observe that it is coordinated via its sulfur atom, okay, to the metal center. So then the only difference will be, just 1 minute. Okay, so those are the cases. So linkage isomers are generally identified by their distinguishing vibrational spectra or the electronic spectra. You can see as the coordination zone donor atoms are changing, so the color might be different, and as well you can just think of that if it is coordinated via sulfur, then whatever stretching frequency in the FTIR spectra you might get, like the CS stretching frequency, let us say, and the C triple bond N stretching frequency, we are just going to observe. If it is coordinated via the nitrogen or if it is coordinated via the sulfur, then we are going to observe this CS and C triple bond N stretching frequency differences occurs in both cases, and therefrom you can have some idea. So here, okay, the vibrational spectra can give you vibrational spectra. Vibrational spectra means the infrared spectra, okay, infrared spectra, or simply Fourier transform infrared spectra we usually say. And from the infrared spectra, okay, we get spectra means this is the plural, or it will be the spectrum, okay, if it is for one compound. But spectra means that is the plural one. So from the vibrational spectra of these two complexes, you can easily get some idea whether it is coordinated via the nitrogen or via the sulfur donor atom. Okay, so this is then the linkage isomerism. Now I am just coming to the stereoisomerism. Stereoisomerism.
Sir, we have another from 12.
You have another class? Okay. Okay, then I will continue the stereoisomerism from the next class. Is it okay?
Yes, sir.
Okay. No problem then. Then you can leave, huh?